Okay, we're going to solve another differential equation using the method of Laplace transforms. Again, like the last example, the Laplace transforms are not the best method for this differential equation. I've got a second order, linear, constant coefficient, non-homogeneous differential equation with x as the dependent variable and t as the independent variable. You know how to solve this one using a characteristic polynomial and then undetermined coefficients. So again, if you're given your choice of methods, Laplace transforms is not the best method for this differential equation. We want to practice using Laplace transforms on a problem like this so that when we get to the ones where we really need Laplace transforms, because there's something weird in the problem, we're ready to handle those. Okay, so Laplace transforms, you want to start by taking the Laplace transform of both sides of the equation. I'm going to use the linearity property on the left side. So I've got Laplace transform of this first term. And so I'm chunking this term by term. That's one of the parts of the linearity property. And then the other part is about pulling the constants out front. So 4 times the Laplace transform of x prime plus 8 times the Laplace transform of x. And that's going to equal the Laplace transform of e to the negative t. Okay, so this step you don't necessarily have to write down, but it can be easy sometimes to lose track of where you're at in the problem. So at least for the beginning, I would advise writing this step down. Then you're going to use your table of Laplace transforms to actually find all of these Laplace transforms. Maybe at this point you've done enough, or maybe not yet, that these order of derivatives that are those terms, you might know those already. But if not, you look them up. So for the second derivative, that's number 23 in my chart here. It's got little f of t instead of x of t. So I'm going to have to pay attention to the variables here. But it tells me s squared. And then it says capital F of s. So again, I've got x for my dependent variable, so capital X of s. So that's the Laplace transform of my lowercase x minus s times x of 0 minus x prime of 0. So in the table, it's got little f here instead of little x. Again, it's important to distinguish between your capital X and your little x, which is why I put this little curl on the end of my lowercase x. I don't always write them that way, but it can be easy with an x to sort of get the wrong one so that you're not sure what you're doing there. All right, and then plus 4 times the Laplace transform of x prime. So that one's number 22 on my sheet here. S times capital S x of s minus s little x of 0. All right, so that's Laplace transform of x prime. And then plus 8 times the Laplace transform of lowercase x. Again, that's what the capital X represents. It's the definition of what this symbol represents in this problem. All right, and then equals, and then this is one I'll look up on my table here. So that's number 5 on the table with a equals -1. So 1 over s minus -1 will be s plus 1. All right, so I looked that up on the chart. Okay, so take the Laplace transform of each side, use that linearity property. We've done that. Now I'm going to simplify that, and my goal here is going to be to solve for capital X and then do the inverse Laplace transform. It's all the steps in the middle of getting ready to do that are kind of tricky. You're going to substitute in your initial conditions. You can really do that at any step, but after here, I'm going to have a lot of stuff drop out on this problem. So it's to your advantage to do that as soon as possible after you've taken those Laplace transforms. So here, both of my initial conditions are 0. So we've got a bunch of terms that drop out on the left side. So let me go ahead and write that down. All right, so that's all I'll have left on the left side. And then equals 1 over s plus 1. Okay, so now I need to factor out the x, the capital X, and divide through by what's left, and then do whatever algebra is necessary so I can do the inverse Laplace transform. So when I factor out the capital X, I'll be left with s squared plus 4x plus 8. And so when I divide through by that, we'll have 1 over s plus 1 times s squared plus 4s plus 8. So in the last example we looked at, there was a quadratic expression on the left side, but that factored more. In this one, this quadratic expression here does not factor anymore over the real numbers anyway, not unless you use imaginary numbers. So we would say that this is an irreducible quadratic expression here. So when you set up your partial fractions for a problem like this, you have to set that up a little bit differently than we did in the last example. The other issue is thinking about doing that inverse Laplace transform. Even if you can do the partial fractions part, how do you handle the inverse Laplace transform? There is nothing in your chart that has something of this form, s squared plus bs plus c, or something like that. So what you want to look for, though, in your chart is the ones that do have irreducible quadratic, or at least quadratic expressions on the denominator. And there are a few, 6, 7, 8, 9, 10, 11, 12, 13. Those all have quadratic expressions on the denominator. And in particular, I'm going to write down the form for number 8 over here. For number 8, it says e to the a t sine of bt, that the Laplace transform of that is b over s minus a, the quantity squared, plus b squared. And so if you look at this and think a little bit about this irreducible quadratic factor on the denominator, maybe you can remember what algebra you could use to force this denominator to be in a form like this. There are also some other ones that have s minus a, the quantity squared, minus b squared. So you could use completing the square to force that denominator in that form. So that's what we're going to do. I would probably do that after you've done the partial fractions, though. So eventually we'll do something, force it into a form like this on the denominator. But I'm going to do the partial fractions part first. So I'm going to go over here and do my partial fractions. So I'm going to have a over s plus 1. And then for the irreducible quadratic factors, that's a degree 2 polynomial. Your numerator is going to be a degree 1 polynomial, bs plus c. So that's a place where a lot of students have trouble, is they write that down incorrectly, and then their partial fractions doesn't work. You don't get a true statement at the end of your partial fractions. So pay attention to what's happening right here. Irreducible quadratic factor on the denominator, generic degree 1 polynomial on the numerator. All right, I want that to be equal to this. And then I'm going to do my partial fractions. I'll multiply through by the denominator. So when I do that, on the left side of the equation, when I multiply this first term, the s plus 1 factor will cancel with the other s plus 1 factor. So I'll be left with a times this second factor. And then when I do that to the second term, on the left side, the s squared plus 4s plus 8 factors will cancel. So I'm going to be left with bs plus c times the quantity s plus 1. Be careful about your parentheses there so you don't forget what's all times each other. And then on the right side, you'll just be left with 1. All right, so again, you do the algebra with the partial fractions to figure out what those constants are. I'm going to set up a system of equations again. We've got some good strategies for solving systems of equations. S squared is the highest power term here. So for my s squared terms on the left side, I'll have a and then a b s squared. And I don't have any s squared terms on the right side. For s terms, I have a 4a. And then I will have a b and a c. So plus bs plus cs when I FOIL that out. And I don't have any s terms on the right side. And then constant. You do not have to label it like this. I do that often just to keep track and so that students can figure out what it is I'm writing these down from. S squared, s, and constant terms. On the left side here, we've got an 8a. And then a c plus c, and that is going to equal 1. So you solve the system using whatever method. This one, I maybe just use a matrix feature on my calculator. And let's see, we will get a equals, what do I have on my scratch paper here? A equals 1/5. Ooh, I hate 5s and problems with s's. So you just have to be careful with your writing there. B equals -1/5, and C equals 3/5. Okay, so there's our constants, and I'm going to put those in here and then prepare to do my inverse Laplace transform. And with these fraction constants, sometimes it's handy to put them out front. I'm going to do that actually on this first one. For this second one, I'm going to leave it here for a second because there's a little bit more algebra I'm going to need to do. So, all right, so for the a over s plus 1, I'm going to have 1/5 times 1 over s plus 1 plus, and then here I'm going to go ahead and put these on the numerator. So minus 1/5 s plus 3/5 over s squared plus 4s plus 8. Okay, so I really have two things of algebra I need to do with this expression. One is I have to complete the square on the denominator. The other is I have to deal with this numerator, which does not match any of the things in the chart for a denominator like this. So whatever order you do them in, sometimes if you don't do them in the most efficient order, you end up having to redo algebra you already did. So I'm going to do this in the most efficient order. It's okay if you don't the first few times through. You will figure out, oh, I should have done that step first because now I'm having to readjust some constants. Every problem's a little different, so you kind of just have to think through the algebra, maybe think 2 or 3 steps ahead in order to see what would be most efficient on that particular problem you're working on. All right, so for this one, though, completing the square on the denominator is going to be the step I want to do first. So I'm going to take half of this middle coefficient, so half of 4 is 2, and square it. So half of this constant coefficient here and square it. Half of 4 is 2 and square it. So 4. 4 is what I want to add in here, which will allow this part to be rewritten as s plus 2, the quantity squared. That's the completing the square part. And then you have to balance that. You can't just go around adding 4s wherever you want. So there are a couple ways you can do that. You can add 4 and subtract 4 in the same expression, and that's not changing the expression. Other way to think about that might be to think about this 8, splitting this 8 up into a 4 plus 4. Notice that's what I'll get when I have the 4 here, and it simplifies to a 4 there as well. Okay, so let me do that step. All right, so the whole point of completing the square is to force it in this form here. So we're going to have s plus 2, the quantity squared. And then these two constant terms will combine to give 4. So that denominator is of this form with a is -2 and b is 2. Be careful there with the b squared. All right, so there are two things in your chart that have a denominator like this, which is what we have here. One of them is this with e to the at sine bt, and then the other one is right below it, I believe, yep, e to the at cosine bt, and the numerator on that one is s minus a. Okay, so I need to force this to be in that form. One of these two forms, or some combination of both of those forms. All right, so essentially what I need to, I'm probably going to deal with the s first here and then deal with the constant. I'm going to do a little scratch work over here with just the numerator, and so that we can save some space and write down what we get when we clean that up and then do the inverse Laplace transform. All right, so this numerator, the -1/5 s plus 3/5, the first thing I would probably do is factor out the constant in front of the s. Notice that this does not have a constant in front of the s. So I'm going to factor out a negative 1/5. Be careful when you factor out the negative, right? Okay, so there's what I got when I factored out the negative 1/5. Now, what I really want here in this parentheses is not minus 3. What I really want in the parentheses is plus 2, so that the numerator and this factor on the denominator match. So I really want a plus 2 in there. Well, in the same way we forced something to be what we wanted so that we could complete the square, you can do the same thing here. You just need to balance it. So if I want this to be a plus 2 in here, I can do that by adding 5 and then subtracting 5. So I'm going to add 5 and subtract 5 in there. The reason I added 5 was to force a plus 2. The reason I subtracted 5 was to balance it. And I was careful to do that in that parentheses because I have this constant out front. All right, so this part will be s plus 2. And then I have this minus 5 here. I'm going to go ahead and distribute this minus 1/5 to this minus 5 out here. So I'll get a plus 1. Okay, so what that tells me is that if I take this last term here on my numerator, this last big old fraction, I'm going to, if I was going to write up my work very neatly, I should probably just write another line with that, but I'm going to run out of space and you won't be able to see what I'm doing. So instead, I'm going to just cross this one out and I'm going to replace it with this on the numerator, and I'm going to split that. So I want one fraction with s plus 2 on the denominator. That's going to have a coefficient of minus 1/5 out front. And the denominator is going to be this completed square. And then the other fraction is going to have a numerator of 1. So I'll have 1 over that. You are getting an algebra workout in this problem. And these are the easier ones. Okay, so you're going to get good at this, though. It's not that hard. It's just algebra. Okay, so this one is ready to go. I can do an inverse Laplace transform of that. That matches something that's in my chart. This one is now ready to go. It matches this. Right, I just have to make sure I'm clear about what the a and the b are. This last term is not quite what I want it to be. The denominator is of the right form, s minus a, the quantity squared plus b squared, but I don't have the right constant on the numerator that I would like to be there. I would like this numerator to be a 2. So again, you can make it a 2. You just have to balance that appropriately. So I'm going to multiply by 2, and then out front, I'm going to multiply by 1/2 to keep that balanced. Okay, so we're now ready to do the inverse Laplace transform. So this is the fun part, because now really all you got to do is write down the answer. Okay, so inverse Laplace transform of capital X is lowercase x. Use the linearity property of the inverse Laplace transform on the right side. So you're chunking it term by term. Your constants are going to come out front. This 1 over s plus 1, that is on your table as number 5 with a equals -1. So e to the negative a t, oh, a is -1. So negative, whoops, e to the at, so e to the -1 t. And then we cross that out and replace it with this, so minus 1/5. And then here are these two. They're up here. I wrote them down, or they're on your table there. So this one is this cosine one with, let me write the a values up here. A is -2. And b is 2 on this one. All right, so don't forget the 1/5 out front, or I have too many markers. Minus 1/5, that's there. And then e to the at, so e to the -2t, cosine 2t. And then for this last part here, plus 1/2. And then this one is what we've got here also with a equals -2 and b equals 2. So e to the -2t sine 2t. So there is our solution to the differential equation. since we did some modeling problems with spring mass problems with equations that represent this, you might be able to think about that in terms of this could represent a spring mass problem where we've got an external forcing function of e to the negative t. And you can see here that we've got some bouncing controlled by the cosine 2t and sine 2t terms with decreasing amplitude. Right, so this part here would represent the transient solution for that spring mass system, which eventually approach zero. And then the steady solution would be what's represented by this. So 1/5 e to the negative 1t. All right, so we're going to look at some that are a little bit more complicated after this section. So going forward, we're going to look at some that are a little bit more complicated for several reasons. Some might be that I might have an unknown function in a particular space where I can't maybe use some of the methods we did before. Some might be where I have discontinuous functions, something controlled by a switch, where something switches on or off. Other things might be just sort of strange functions that model important real-world phenomena, but things that are not easily described by just kind of the ordinary functions that we're used to working with. So after this section, you're just kind of getting an algebra workout here in this section and trying to understand the whole process. But after this section, we're really going to start working with the ones where Laplace transform really is the best method to use to solve those. So make sure you do those so that when we get to those harder problems, you're ready to handle all the messy algebra.